This live session. I'm Hisham Mukhtar Ali, Senior Reservoir Engineer for almost 12 years experience in reservoir characterization, reservoir management, and simulation. As mentioned in the introduction of this session, it's designed to cover a quick overview for the operation of field operation of coring process, the comparison between whole or full diameter core and sidewall coring operation, and then an overview of conventional or basic core analysis workflow, and then the interpretation and analysis of RCAL data to select the specific core samples or core blocks to start your special core analysis program. And then we will highlight the applications of SCAL data or special core analysis data, specifically the relative permeability and the capillary pressure measurements, and finally some case studies and field applications. So starting directly with our agenda in this session. So overview of coring operation, then core analysis workflow, starting with the conventional core measurements, and the applications of RCAL or conventional core or routine core measurements to identify reservoir flow units and reservoir rock typing. And then we will start to cover an overview of special core analysis measurements, starting with relative permeability data and using of normalization and averaging procedure, and then the applications and different measurements techniques of capillary pressure and applications of capillary pressure data to identify pore road size distribution, and also the applications of saturation height modeling process, and finally an overview of Archie saturation parameters for water saturation calculations, and applications of core data, specifically resistivity index and resistivity factor measurements. So as a very common introduction for petroleum engineering, generally it applies its scientific principles to quantify, to characterize the fluid flow through the porous media for the subsurface reservoir and the entire production system during the development and the production of oil and gas assets. The objective is to achieve the highest ultimate recovery. Reservoir characterization is an important part of this process to understand and to clearly identify the reservoir rock and the fluid parameters. This is actually the concern of our session. Other activities or applications for such a discipline is to identify how much oil and gas is originally in place, the driving mechanism, the prediction of production rates, and so on. All of them based on the proper reservoir characterization for fluids and reservoir rocks. The reservoir system, as you can see, we have two basic elements. We have the rock metrics or grains of specific lithology, maybe clastics or carbonates or mixture of them, and certain cementing material. And in between, we have some pore spaces. We have in these pore spaces the mixture of or combination of reservoir fluids, mostly water plus a type of hydrocarbon, maybe gas or oil, or mixture of gas and oil. Characterization of reservoir rocks and the interactions between rocks and fluid is typically the major concern and the objectives of core data measurements and core analysis and core data interpretation. For reservoir rocks, as you can see, it's important to identify the pore geometry or pore throat size distribution, basic rock parameters like reservoir porosity, permeability, fluid saturation, special core measurements like capillary pressure and relative permeability that control the relative movement of different phases at the reservoir pore scale, and also identify the fluid distribution throughout the reservoir. Also, determination of pore throat size and pore throat size distribution is an important application for rock data or special core analysis data. Also, the mineral composition of the reservoir rocks is very important to identify the types of clay and clay minerals and the importance of the clay minerals and their interactions with the completion and drilling fluids and so on. Also, the cementing material, is it what's the type of cementing material, carbonates, sulfate, or silica, and so on. This is also an important process for rock characterization, combined with the fluid characterization, which is not the concern of this session, but it's simply the applications of reservoir fluid data or PVT data and flow assurance analysis for the water phase and hydrocarbon phase. Typically, the fluid composition and the fluid properties are the most important measurements to be characterized. So if you look at the entire petroleum production system, as you can see, the first element of this system, as you can see, is the reservoir itself or the porous media. Determination of reservoir parameters, firstly, the rock properties and also fluid properties, and the most important part is the interactions between the rock and the fluids in terms of rock wettability and other parameters like capillary pressure, relative permeability, and so on. So this is the core data analysis and the core measurements are applied to this element of this part of the petroleum production system, as you can see, which is the porous media. Other elements like the vertical lift performance and surface network, this is the all of them must be integrated together. So for proper reservoir management and reservoir characterization is it's related to the proper data acquisition and data analysis. As mentioned, we have two major elements, reservoir fluids and reservoir rocks, and the combinations of rocks and the fluid together, which is defined as the petrophysics or petrophysical analysis of reservoir rock and the fluids using the wireline measurements of well logging data, which must be integrated with the core measurements as well. So all of them, rock and fluids and petrophysics, must be integrated together for proper reservoir characterization and powerful reservoir management and reservoir development plan. So the workflow is typically is to plan for the characterization requirements and data to be acquired, and collect and analyze the data, maybe for production, within production, or during production, and so on. Mostly, as mentioned, coring and core data, fluids, and logging they are most important for reservoir characterization process. For the if you look at the EMB project life cycle, starting from the exploration phase to the appraisal and development and maturity phase, you will find the appraisal phase is concerned with the field studies, geological studies, reservoir study related to understanding reservoir rocks and fluids. So looking at this plot, we have on y-axis we have cash flow against time. So we have four major parts or phases of the field development, starting with the exploration phase, which means the reservoir parameters is not highly defined. So as you can see, the cash flow is typically negative due to we have high invested capital cost due to the exploration and license acquisition, seismic acquisition, seismic processing, and so on. Once we have a successful exploration, so you can start production somewhere right here. So once you have significant discovery and commercial discovery for hydrocarbon system, and you can start production. So you will start the second phase, which is the appraisal or the delineation phase. As you can see, the cash flow starting to increase, like this trend, which is production build-up. So for this phase, the coring and the core analysis and the core studies are essential during these two phases, the exploration and the appraisal phase, mostly during the appraisal phase, to clearly understand the reservoir mineral composition, reservoir rock properties, reservoir fluid and rock interactions, and reservoir dynamic properties, typically relative permeability and reservoir fluid distribution by the capillary pressure measurements. So the next phase is the development or production build-up phase. As you can see, it's we have the highest production can be achieved from a specific field. The objective is to extend this phase as much as we can. And finally, the maturity phase, we have clear production decline or pressure depletion. So the objective of reservoir management in this phase is to extend the reservoir lifetime as much as we can to maximize recovery and using the optimum reservoir development plan or depletion strategy. So this is simply the EMB project life cycle and the importance of coring and core studies during the appraisal phase before after exploration and before the development phase. So for reservoir characterization process, so all of the subsurface data and production data are important regarding production testing, core analysis, wireline logging, seismic data, interpretation and integration of, and also correlation of all of these data together, so you can get proper characterization for reservoir fluids, for the reservoir geology and the reservoir rocks. So as mentioned, mostly the relative permeability and the capillary pressure data are controlling the most important reservoir parameters and interactions between different fluids, and also the reservoir fluid distribution and so on. So by integrating fluids reservoir geology and rocks together, so you can identify the key reservoir opportunities, identify main driving mechanism, also determine the reservoir volumes or initial hydrocarbon in place, and also can be used to monitor the reservoir performance, and finally can set the optimum reservoir development decisions. So as a rule of petrophysics, as you can see, it's an integrated process for all of the available data from subsurface. Using the first data can be obtained from a specific well, mud logging data, borehole seismic data, also core data, and wireline logging measurements, maybe open hole or cased hole, also reservoir monitoring, logging, and field studies. Integrating all of them together with interpretation and quality check and uncertainty analysis, you can start to set to calculate reservoir volumetrics and build your static reservoir model, and start to define dynamic model parameters. So the detailed process, as you can see, the first step is the geological and geophysical assessment regarding the regional geology, reservoir structure. Core description is important in this phase, the positional environment and the reservoir stratigraphy. The second stage, petrophysical evaluation, like reservoir rock typing, post-road size distribution, reservoir fluids, and hydraulic unit type. All of them, actually, as you can see, they are integration between wireline measurements and core measurements. So in this stage, petrophysical evaluation, the core data and core measurements are very important for accurate and proper reservoir and petrophysical evaluation. So next step is the complete formation evaluation for the saturation determination, permeability profiles, hydraulic flow units, and also reservoir compartments. And final stage is the reservoir modeling by integrating all of previous stages, and also using the production data and well and reservoir models. So this data can be used to control the parameter distribution, the distribution of porosity, permeability distribution throughout the 3D reservoir model, and also the initial water saturation distribution, and as an input process and for dynamic reservoir modeling. So value of core analysis studies and core data, as you can see, they are very important almost for all disciplines. As you can see, for even slab core, we can get core photographs, sedimentology, lithology. Also for thin sections, we can get important details regarding the core structure, porosity types, depositional and environment, and also the XRD analysis, mineral composition, SEM. Also where the routine core measurements, including porosity, permeability, grain density, and as received saturation, and special core analysis data, as mentioned before, the relative Permian capillary pressure, electrical properties, or Archie saturation parameters, acoustic properties, or compression, clay chemistry, and so on. Also, we have advanced core studies like geomechanics and geochemistry. They are also one of the values of core measurements. So value of core data in reservoir simulation. As you know, and very quickly for reservoir simulation modeling, the first step is to build a 3D static model using the basic rock properties to calculate pore volume and transmissibility of each 3D grid or 3D grid cell defined in grid and edit section. The value and applications of rock physics integrated with reservoir fluids. You can define porosity, conventional and special core analysis data, and to initialize your model and calculate the initial saturation in your 3D grid, and identify pressure and initial pressure distribution, and calculate the in-place volumes, and also calculate the reservoir flows using the measurements of relative permeability to calculate gas oil ratios, water oil ratio, water cut, and other production parameters in case of we have multi-phase flow in at the reservoir conditions. So value of core data is actually defined in this step for the at the model initialization and calculations of the in-place volume, pressure, and fluid distribution, and also reservoir flows. So for reservoir simulation, you can integrate of all of inputs together from petrophysical analysis, petrology and mineralogy or sense sections, porosity, permeability, and rock types must be integrated with the rock typing defined in the 3D reservoir model. Relative permeability data to control the relative movement of different reservoir fluids, and capillary pressure data to identify the initial fluid distribution and initial water saturation distribution for the 3D grid. So in this short video, as you can see, we can highlight the importance of special core analysis data for both scale displacement and understanding of the reservoir rock and fluid interactions for improved oil recovery applications like water injection or even gas injection or enhanced oil recovery. All of this data for proper and controlled EOR and applications must be combined with proper reservoir rock characterization. This is related to the understanding of how to minimize the residual oil by understanding the type of wettability of your system and the relative permeability, and how to control the mobility of different fluids to maximize recovery by secondary or even enhanced oil recovery techniques. So simply the core is simply as a cylindrical shape, as you can see, of reservoir rock. It's actually it's considered a microscopic sample of the entire reservoir relative to the reservoir scale. This core will help us to evaluate the rock properties and identify the reservoir mineral composition and textural, both road size distribution and other fluid rock interactions. While the coring is the process of cutting the required core material like this, using specific equipment cut at well site, maybe during or after the drilling operation. So simply during the drilling operation, it's considered the full diameter core like this. But after drilling operation, it will be sidewall coring operations. So coring operation can be full or whole diameter core like this one. This is a full diameter core, and it's like a cylindrical shape or rock sample of reservoir based on the hole size. And we have a certain coring string like this with a specific core barrel designed for cutting this core based on the rock types and lithology. The core will be cut in several lenses, maybe 30 up to 60 or 90 and so on foot long. So the core, as mentioned, is cut in certain core barrel, which is a hollow pipe designed in this core string. While sidewall coring process, it's a wireline technique can be used to acquire certain core samples at specific depths. It's typically a more cheap technique for obtaining core samples and rock samples from a reservoir at certain depths using a coring gun. The coring gun is typically like the core barrel designed to acquire a small diameter and small length core sample or rock sample. So this is the comparison between the drilling bit like this. It's designed to grind away the rock cutting by the circulation with the circulation process, while the coring bit like this, it's a hollow pipe which is designed to acquire the full diameter core inside this barrel. So the coring bit is designed with like two dial face with a fixed cutter like this, while the center of this borehole is of the acquired core will be untouched. The hollow bed creates a cylindrical shape of the core like this. So while the full diameter coring operations, the well site geologist must be closely monitor the drilling progress to make controlled drilling, and by log correlation with the offset wells and evaluating and monitoring the mud logging data, the well site geologist can identify the top of the coring section and the location of coring point to start the coring operations. So this is simply, as you can see in this video, we have the major elements of coring, conventional coring barrel for acquiring side for full diameter core. So we have some elements like being assembly to maintain stability while the coring operations and minimize vibration. The other element right here, which is the special assembly to ensure the high quality core without certain fractures. To start the coring cutting, you have to drop this ball from surface, and then the coring bed will start to cut the core, as you can see, for a certain section or certain length as per the coring design. Once this is the application of this section to reduce the vibration, and once the core section is acquired, as you can see, this part of the coring string will catch the core section and will start to pull out of hole with this core section to surface to start the preservation and transportation of the acquired core. For the sidewall coring, as you can see, it's in a certain design strength to acquire certain sidewall cores with small diameter and small length. The sidewall coring strength can acquire up to 90 sidewall core samples from a single well run, as you can see. So this is the process of sidewall coring. As you can see, this is the coring gun. The coring gun will based on selected coring points. It will use the wireline measurements like gamma ray to correlate this coring depth and start to cut the core at a certain point at a specific depth and so on. This assembly is a string of sidewall coring, as you can see, some mark of Schlumberger's for sure core, and this is the string of this string at surface. So this is the coring gun at the surface as quality check before starting to run in hole with this string. And this is the process of expanding this core gun and starting to cut the sidewall core at certain depths. So routine, once the core is acquired, maybe full diameter core or sidewall core, the core will be preserved at well site and transported to the core lab. In the core lab, we have a specific workflow for routine core measurements, starting with the core log depth matching to correlate between the acquired core depths and the well logging data and wireline measurements, and then core selection and plugging to select certain points or certain depths to cut certain cores to start your routine core measurements, followed by cleaning and drying for core samples and direct measurements of core density, porosity, and helium porosity and nitrogen permeability. And once we have routine core data, so core porosity and permeability data analysis is the next step by cost plotting and data interpretation for rock typing and classification of reservoir flow units, and to identify the different petrophysical groups. And finally, we can apply a certain model to predict the permeability from logging data you calibrated by the core measurements. This is the receipt of core at core lab. As you can see, this is the sections of core. The core is cut into sections, as you can see, like 1 meter. And the core at the core lab will be once received will be stored in this cylindrical bottles and opened to start core slabbing and core cutting and the required and next workflow. So the generalized routine core workflow is receipt of core at core lab, core layout and markup, then the core gamma ray for log and core depth matching, and then plug sampling or core sampling, followed by gas permeability, helium porosity, and grain density. This is the basic routine core measurements. And for slabbed core, we can make a white core photography using white light and ultraviolet light for the slabbed 2 to 3 sections. And finally, the fluid saturation may be due to different techniques like we taught or Dienstag process. The core log types matching, as you can see, is a very important process to ensure good correlation between the core and logging measurements, because for the later on applications for core data is to calibrate the logging measurements using the core data. Core photography is an important step, can be used to identify the hydrocarbon potential and carbon presence of the core, specifically the ultraviolet light, and can be used to detect some features of core light fracturing, like fractures, bugs, and so on. The RCAL measurements, as you can see, simply you can have the cross plots of core porosity, permeability, and such histograms of porosity distribution, horizontal permeability distribution, grain density, and the range of permeability, as you can see in this quasi permeability it's actually tight reservoir. Maximum permeability is almost 3 millidarcy, but the porosity, we have porosity up to 28%, but for the grain density, as you can see, the range from almost 2.7 up to 2.76 gram per cc, but the mean core grain density, as you can see, it's 2.71, which is the grain density of limestone. So another application of RCAL measurements is reservoir zonation and rock typing. So using the porosity and mobility data and other special core measurements like the capillary pressure, mostly the mercury injection and porous plate capillary pressure measurements will be highlighted shortly in this session. Here we have an overview of different reservoir zonation and rock typing techniques. Actually, we have several techniques to identify the reservoir flow units and rock types. All of them actually is dependent of these three equations: the RQI, reservoir quality index, which is totally a function of porosity and permeability measured in the routine core phase, and FZI, flow zone indicator, which is a function of RQI, and phi z. Phi z is the normalized porosity. So all of these definitions are functions of only porosity and permeability. So using this raw data like this, we have this typical cross plot of permeability against the porosity on this similar plot, locate on y-axis against phi. So as you can see, we have different hydraulic flow units or dynamic rock types for this system, as you can see, based on the other techniques like this one, the FCI probability plot. In this plot, we have typical and normal probability plot, which is FCI against the cumulative probability. The concept very quickly is dependent of each reservoir rock type or flow unit will have a certain line with a specific slope. So as you can see, we have flow unit number 1 defined by this part. We have a clear difference in the second part for flow unit number 2 and flow unit 3 and so on. This is the application of FCI probability plot. Also, we have another technique, which is the log-log plot between RQI and phi z plot. It can be used to calculate the mean FZI for each reservoir rock type or hydraulic flow unit. Also, we have this widely used technique, which is Wetland R35 technique. It's an widely used technique to classify the reservoir units based on the size of pore throat, from the nano pore to maybe micro, meso, and micro pore, and so on. And this is the dominant pore throat radius at R30 at 35% saturation mercury. So for this one, we have the dominant pore throat radius is 30 micron, as you can see, but this one, the lowest quality reservoir rock unit, we have the dominant pore throat radius is 0.1 micron. As you can see, the permeability range, it's up to 0.1 millidarcy, and covering wide range of porosity, as you can see. Also, we have this widely used equation to define hydraulic units or dynamic rock types. It's totally a function of the FZI defined by this equation. So this is some of the techniques can be used to identify reservoir rock types and flow units. This is another levels of reservoir zonation, as you can see, using Wetland R35 technique, like this another core, and this is the detailed subdivision of reservoirs, you can see, but mostly we have to classify the reservoir flow units based on the defined features and defined rock types in the 3D reservoir model, because we will apply the defined transforms between permeability and porosity in the 3D graph. So in the 3D reservoir model, you will have a static reservoir model or 3D grid. In each grid cell or grid block, you have to have a defined porosity, and based on specific porosity distribution. So you can use these defined transforms or defined relationships between porosity and permeability to calculate the permeability for each grid block for every rock type or every defined features type in the 3D grid. So also in the integration between routine core measurements and petrophysics is very important and must be calibrated to using the core data. So in this reservoir, as you can see, we have high quality sand, as you can see, for this two bars, which is hydraulic unit number 4 and number 3. But for this hydraulic unit 1 and 2, we have this part, which is the salty part in between, defined by high gamma ray and low resistivity, and also this reduced neutron porosity, as right here, as you can see. This is the related to hydraulic unit number 1 and number 2. Once we have complete interpretation and analysis of routine core data, we can assign a specific SCAL program to select certain depths to start the special core measurements. Simply, the SCAL program, once the samples are selected to cover all of the flow units and rock types, so we can start your SCAL program. As you can see, mostly we have the basic measurements, starting with the wettability measurements. High pressure mercury injection can be applied on the small samples or in the trams. And for the saturated sample, we have three basic measurements: the relative permeability of core flooding, the capillary pressure, maybe gas, oil, water, oil, based on the types of fluids at the reservoir conditions, and also the electrical properties like formation resistivity factor and resistivity index. And finally, we have the final SCAL report. Now I will highlight on some of the special core measurements, starting with the permeability definitions. Mostly, as you know, we have three definitions for permeability. The first is the absolute or specific permeability, which is defined the capability of the porous media to transmit fluid. If this media is 100% saturated with a single phase, defined by Darcy's law, as you can see at the reservoir at field units. But actually, the porous media is not 100% saturated with one phase, but actually we have more than one phase at the reservoir condition. At least we have two phases. So we have a new definition, which is the effective permeability. So if the porous media is saturated with more than one fluid, so the effective permeability of oil is the permeability to oil in the presence of other phases like water and gas, and maybe gas and water and so on. So the applications of effective and maybe relative permeability for reservoir simulation model, and any multi-phase flow calculations at reservoir conditions, relative permeability must be defined. Also, the estimation of residual oil saturation is on all of them applications of relative and effective permeability data. For the relative permeability, it's defined as the ratio between the effective permeability divided by the what we call base permeability. So this base permeability can be the absolute permeability, or can be the effective can be the effective permeability to oil at SWI, or the effective non-wetting phase saturation at irreducible wetting phase saturation. So the permeability measurements, we have, as mentioned, we have three definitions. So and we have some sources of permeability, as you can see. So well testing interpretation can be used to identify the average effective permeability of the reservoir. And well logging interpretation can be used to calculate the absolute permeability using NMR logging measurements. But the core measurements at core lab can be used to calculate the absolute permeability, the effective permeability, and also you can calculate the relative permeability. So the laboratory core analysis is the best application for the different core different permeability measurements, including absolute permeability, effective, and relative permeability. So this is the typical oil water relative permeability curve. As you can see, we have relative permeability in y-axis for oil and water against water saturation in x-axis. So on the water saturation is increasing from 0 to 100%. In the same direction, we have increase in the KRW for this curve. And on the other direction, we have increase in oil saturation, so the curve of oil following this trend. So for any relative permeability curve, as you know, we have 4 different endpoints. These points highlighted in the yellow circles. The first one is the SWI, reducible water saturation. Second point is KRW at SOR, the relative permeability to water at residual oil saturation. On the other direction, we have SOR, or residual oil saturation, at this point. And last point is KRO at SWI. So once you have KRO equals 1 or 100%, that means the base permeability is defined as, according to this definition, is defined as K effective oil at SWI. That means the 2 values will be the same. So KRO at SWI in that case must be equal 1. So applications of relative permeability data for the immiscible displacement calculations for the design of water flooding application and immiscible displacement, like gas injection or water injection and so on. So in that case, relative permeability data are very important, and we can calculate what we call the fractional flow of water, and using different displacement techniques like the fractional flow equation defined by Leverett and frontal advance equation defined by Buckley-Leverett. So we can characterize the expected recovery from water flood project and so on, like this case. So we have the raw relative permeability data average curves, and this yellow color, this is KRW, and in the green color, this is the KRO, and this curve in the here we have the fractional flow of water based on the interpretation of this fractional flow curve. So we can estimate the average water saturation behind the flood front for water injection evaluation, and also the oil recovery at the peak throw using this technique, which is totally dependent of special core measurements or relative permeability data. So as you can see, mostly we have different relative permeability curves for different rock samples and core samples. So these curves must be normalized and averaged to get single curve representing a specific rock type or specific fishes. So this is the lab measurements. Smooth curves, and then these curves are subjected to normalization process to convert saturation and relative permeability SW star KR star from 0 to 1, and last step is the denormalization to get an average curve for all of these blocks together. So we have finally one curve representing all of these core samples. So in this example, we have, as you can see, we have 3 different core samples, and this 2 curves in the bold yellow, blue color and green color. This is the average curves representing all of these 3 blocks. They are matching the SWI, SOR, KRW at SOR, and KRO at SWI. Also, the relative permeability data can be used to identify the type of wettability based on the value of SWI and based on the intersection point between the two curves, but actually the time is not long enough to cover this technique, but this is another application of relative permeability data. Now we have a very important part of the special core measurements, which is the capillary pressure and integration between relative permeability and capillary pressure. Simply, once we have multi-phase flow and multi-phase in the reservoir conditions, so we have to define the relative perm and capillary pressure. So simply, if we have this oil leg and below this oil leg, we may have water zone or water aquifer, but the zone or the contact between this oil and water zone, this contact or this interface is actually, it's not a line, but it's a specific zone defined as the transition zone between oil and the water. This zone and the thickness of this zone and the height of this transition zone is actually controlled by what we call the capillary pressure. So capillary pressure controls the height of the transition zone between oil and water and defines what we call the height above the free water level. So free water level, or FWL, is an imaginary level. At this level we have defined capillary pressure equals 0. So capillary pressure by definition is the difference between the pressure of the non-wetting phase minus the pressure of the wetting phase. So the thickness of transition zone is can be ranged from a few foot up to maybe 300 or 400 foot, based on the reservoir quality and the reservoir permeability. So for the capillary pressure, as you can see, it's an following this trend. In y-axis we have water saturation from 0 to 1 against the capillary pressure curve, increasing from this point, which is the entry pressure or threshold pressure, which is the pressure required to force the non-wetting phase like oil into initially wetting phase saturated pore, which is the largest pore at this point. Once the pressure is increasing, as you can see, we have a reduction in oil and reduction in water saturation down to this value, or SWI, or irreducible water saturation. So capillary pressure or cap pressure and well perm curves, we can use these two measurements to characterize the transition zone between oil and water zone, and the thickness of this zone, and accordingly the oil dry limit, and also the capillary pressure can be used to identify different rock types. So the high quality rock types is defined by the sand transition zone, as you can see, like rock quality or rock type number 1, and low SWI, but the low quality reservoir rock, like rock type number 3, we have thick transition zone and high SWI, as you can see, and also the high entry pressure relative to rock type number 1. So in reservoir simulation terminology, we have what we call the saturation functions. Saturation functions are defined as the combination of relative permeability and capillary pressure to define the initial saturation distribution at reservoir condition at initial reservoir condition by the capillary pressure curve, and to define the relative movement of different phases for oil and water also at a reservoir condition by the relative permeability curve. So capillary pressure is, as mentioned, is the pressure at the interface separating two immiscible fluids like water and oil. It's as mentioned before, the pressure difference between the non-wetting phase and wetting phase, defined as a function of these parameters, which is the oil-water interfacial tension, the contact angle between oil and water, and the capillary radius, or the radius of the capillary tube. So simply, as you can see in this capillary tube experiment, the capillary pressure is the highest in the small pores or small capillary radius, but the capillary pressure is minimum if we have large pore throat radius and large capillary tube radius, as you can see. So the first step for capillary pressure calculations is to estimate the level of free water or free water level, which is the interaction between the oil gradient and water gradient lines, using the pressures in water and oil zone and the pressure in oil zone. And next step is to calculate the height above the free water level using this equation. So if we have this simulated model, we have the injected water at this side, as you can see, and this is the capillary tube representing the post-throat radius. So this point on the capillary pressure curve is the entry pressure. This is the pressure required to force the non-wetting phase in the green color into initially wetting phase saturated pore, or the largest pore, this one. This is the first point in the capillary pressure curve. Second, the oil will be forced into pore spaces or pore throats or capillary tubes with smaller radius, like this one, this second point. And for this point, we have the oil is injected in more smaller capillary tubes like this one and this one and so on, which means the oil is forced in more pore spaces with smaller pore throat radius. But for this point, this is the maximum capillary pressure, or the minimum water saturation or reducible water saturation. So the this is the maximum achieved reduction in the water saturation or the reducible water saturation. As you can see, we have some very small pore throats or very small capillary tubes are still not forced by the injected oil, even at higher capillary pressure. So this is the simulation of the capillary pressure curve between the oil and water. So identification of the free water level, as you can see, using the pressure measurements. So bottom hole pressure data correlated with the wireline logging. As you can see, if you look at the resistivity data, we have high resistivity for this part across this oil zone, and we have gradual reduction in resistivity, defining this low quality part of the reservoir and 100% water in this part, and this is the transition zone right here, defined by the gradual reduction in resistivity for this section. So we have pressure points selected at these depths, as you can see in the green color, and we have pressure gradient 0.42 psi per foot, which is water gradient, 0.43 psi per foot, which is water gradient. And for this part, we have 6 pressure points with gradient 0.37, which is the oil gradient, and the intersection is almost at this depth, so maybe right here, which is the level of initial oil water contact, or the free water level. So this is the terminology of capillary pressure measurements. We have 100% water for this part, and the top of this water is the free water level at 0 capillary pressure, and we have this zone, which is the oil water contact mostly above the free water level by very few foot, and this is the height or thickness of this transition zone is controlled by reservoir rock properties and the reservoir quality. So for high quality rock and high permeability, the thickness of this transition zone will be minimum, but for tight reservoir or low quality reservoir rocks and low permeability, the thickness of the transition zone will be much higher. So capillary pressure is defined and is required to calculate the initial hydrocarbon in place by estimating the SWI, and also the distribution of fluids as a function of the height above the free water level. And also the capillary pressure is required to describe water flood behavior in case of we have very complex reservoir systems. Capillary pressure is highly correlated with reservoir rock typing and reservoir bore throat size distribution. So the high quality reservoir or large bore throat radius, we have minimum SWI and minimum transition zone, but a small bore throat radius and capillary radius, as you can see in model C, we have very high SWI and very thick transition zone. So this is an actual measurements, as you can see. It's an A-point capillary pressure curves. So for this one in the red color, this is the permeability is almost 420 millidarcy. So the SWI is almost 18%. But for this one, we have permeability, the highest permeability, 5 darcy. As you can see, the SWI is almost 6%. So this is the direction of permeability increase, and also the direction of SWI decrease. So the wettability is an important parameter and important scale measurement. Wettability is the tendency of the porous media to the fluid to wet the rock surface, maybe oil, wet, water, wet, or mixed wettability. But we have to define the two different processes. The imbibition process is defined as the increase of wetting phase saturation. That means we have oil displacement by water if we have water with rock, but the drainage process in that case we have the increase in the non-wetting phase saturation in case of oil displacement by water, but we have oil with rock. So we have different trends or different definitions of capillary pressure curves based on the saturation history. In this one, we have the primary drainage process in the starting from 100% water to SWI. But this one, we have the imbibition process. We have increase in wetting phase saturation, but can't be achieved the 100% water because we already have residual oil at this point. As an comparison between the lab measurements of capillary pressure, we have three common measurements. The pore split is in it's a best analog to a reservoir at maybe at confining stress at initial reservoir condition, but the maximum capillary pressure can be achieved is 200 psi. But the disadvantage of this technique, it's very slow, and the measurements can take few months up to 5 or 6 months and so on. Second process is the centrifuge. It's in fast measurements, can handle low permeability reservoir rock samples. And the last technique is the widely used one is the mercury injection mercury injection capillary pressure MICP. It's an actually the major disadvantages of this technique is it has no analog with the reservoir conditions because we have no wetting phase, because this process we have air and mercury as two different phases, so no wetting phase is in the mercury injection lab measurements. But the importance of this technique, it's an fast measurements and low cost, good for rock typing, and can handle small and irregular rock samples and so on. But correction may be required. But the best practice for capillary pressure measurements is to use a combination of the pore split, which is very accurate measurements, one best analog to reservoir conditions, and other techniques like centrifuge or the mercury injection. So this is the capillary pressure data, as you can see, for different rock types. So you can clearly identify the high quality sand in the red color, and the low quality sand in the green color. We have different samples. So the next step for analyzing capillary pressure data is to get the average capillary pressure curve by fitting the data from different core samples. So this is the applications of petrophysical grouping by the capillary pressure data, as you can see. And it must be integrated with the routine core measurements like porosity, permeability, cross plot. And this is the capillary pressure for different samples against water saturation. And this is the post-road radius in micron. So this group of curves representing the highest quality rock type with the maximum post-root radius. This one we have slightly lower quality, and the lowest quality rock typing is here. We have very low post-root radius, less than 0.01 micron. So this is the actual core data from mercury injection capillary pressure. We have 4 different samples. So for this sample in the purple color, we have permeability. As you can see, block permeability is almost 660 millidarcy, and gold porosity. So the post-root radius is almost 7 micron, but this one in the blue color we have the lowest permeability, which is 2.87 millidarcy, and the corresponding post-root radius less than 0.1 micron. So this is the another application of mercury injection capillary pressure data for rock typing and identifications of the pore throat system, and pore type, and reservoir heterogeneity, if we have a dominant unimodal system or bimodal system, and so on. So this is the converted to reservoir condition porous plate measurements, as you can see, and this is the equivalent mercury injection capillary pressure data also converted to reservoir conditions. So as an application of capillary pressure data is the modeling of water saturation for the 3D model, using what we call the saturation height modeling. It's an integrated process between logging and core data. So the recommended approach is to use an integration between initial water saturation from capillary pressure and from logging data, and all of these logging and core data must be calibrated and integrated together to define the initial water saturation distribution for the 3D model. So the process is simple, as mentioned. First, you have to identify the free water level, and by defining the capillary pressure curve, you can identify the corresponding initial water saturation for every grid cell in the 3D model, because the depth of this 3D grid cell is known, so we can calculate directly the corresponding water saturation. But it's very important to validate the correction from lab to reservoir conditions. We have specific workflow to convert the capillary pressure measured at core lab to equivalent capillary pressure by applying specific corrections for stress and closure pressure and so on, and you can get the corresponding capillary pressure curve at reservoir conditions. So this is the water saturation calculation decision tree. As you can see, the recommended approach is to use the capillary pressure by estimating the free water level and using the parameters to calculate capillary pressure, and then you can calculate the corresponding water saturation. Now we will highlight very quickly the capillary pressure data fitting one of the widely used techniques like leverage, Somir function, Fuchs, and Corey lambda functions. As you can see, all of them are functions of capillary pressure and other data like porosity, permeability, the widely used leverage J function, the interfacial tension, contact angle. For Somir model, we have what we call the the FG or G parameter, and the displacement pressure, and also the measured capillary pressure. The widely used technique is the Fuchs and Corey defined using this equation. So it's a function of BD or displacement pressure and this lambda parameter. So the Fuchs and Corey in this equation, we can set this equation as a straight line equation like this definition, as you can see. So this equation of function of SW star, which is the effective wetting phase saturation, BD is the displacement pressure or the entry pressure, lambda is the pore size distribution index. So plotting BC against SW star on this is y-axis against SW star and x-axis on log plot. So the slope of this plot will be the lambda will be the negative the 1 divided by slope, but BD is the extrapolation of this straight line according to this form y equals ax plus b. So this is the comparison between the experimental core capillary pressure measurements and the capillary pressure calculated by Fuchs and Corey model, and this is the calculated by Somir model. So simply the one of these models will be used to fit or to match the lab measurements, and finally this model will be used in your simulation model for simulation applications. So another applications of capillary pressure is to assign the initial flow distribution in the 3D grid, which is the initialization process. So in this model, we have defined gas oil contact at this level and oil water contact at this level. So if you look at this grid cell in the oil zone, this is the clear oil zone, as you can see in the red color, and in the blue color, this is the clear water zone, but in between we have this transition zone. So for this grid cell, we have the oil water capillary pressure equals 6 bar, which is the maximum capillary pressure, but water saturation is equal 0.2, which is SWI. But for if we select one grid cell right here, so the SW equals 0.28, which is value higher than SWI, which means the changes in water saturation from 100% water at this level and SWI or reducible water at the free oil level. And we have this grid cell in the water zone. We have water saturation equals 1, but capillary pressure, this is the minimum capillary pressure. Last part to highlight is the for saturation calculations, we mostly use the Archie saturation model defined by this equation. So we have two different forms to get this final form of Archie model. So this one is the formation resistivity factor defined by the RO is the resistivity of formation at 100% water, and RW is the resistivity of formation water. And second equation is I, or resistivity index, defined by the ratio between RT is the true formation resistivity, and the RO is the resistivity of formation for reservoir at 100% water saturation. So the calculations of resistivity index and the resistivity factor and the resistivity index by special curve measurements will be used to calculate what we call the Archie saturation exponent N and Archie cementation and cementation factor M. So the cementation factor M and saturation exponent N will be calculated using special curve measurements to have accurate calculations of saturation using Archie saturation model for calculation of water and hydrocarbon saturation as an objectives of formation evaluation program. So this is the calculated formation resistivity factor at overburden pressure. So this is the value of M, as you can see, for different plugs. It's less than 2, but actually if it's it can be considered as value of 2, which is a widely used value, but the correct workflow is to be used from the formation resistivity factor measurements. The last part to highlight is which is the application of core analysis, is the core description and core imaging for the zoology determination and fishes depositional environment, structural and elements, the flow distribution, X-ray diffraction, advanced measurements like nuclear magnetic resonance, and so on. Just an application of XRD on core samples at different samples. So XRD analysis provides the percentage contribution of the different minerals as quartz, feldspar, kaolinite, different clay minerals like illite, kaolinite, and so on. So for these 3 plugs, for this one, we have high contribution and high percentage of kaolinite, which is a type of clay mineral, can be promote the mechanism of formation damage. So we have to consider this for water flooding applications and so on using the XRD analysis. Also, thin section, it's provide an description and the mineral composition of the rock, texture analysis, type of porosity, the cementing material, and so on. So in this samples, the solution, as you can see, is a key element for the improvement of reservoir quality. This is a carbonate reservoir. Also, integration between porosity permeability with thin section is important. So this one, we have high permeability rock type, and this is the description by thin section. But this one, we have low permeability rock type, and this is the corresponding thin section analysis. Last part is the SEM. It's a very high magnification of the core sample, so you can identify different types of the post-scale elements, like the mineral composition, like quartz, kaolinite. This is the post rods and so on. So this is the another application of core measurements. So now we have the quick overview of some core reports. We have this report. This is the standard routine core measurement like this. We have depths, core number, corresponding depths, and the values of nitrogen permeability, helium porosity, and also grain density, as you can see, and lithology description. So this is the raw data for any core analysis report. So this data can be used to calculate the fluid saturation like this, and different rock typing techniques can be applied to classify the rock, the reservoir, to different rock types like this technique. This is the application of Winland technique to classify the rock reservoir rock as per different post-road categories. And this is another technique, which is the FCI probability plot. As you can see, we have 3 clear rock units or rock types, and this is the first step of core log depth matching. So in the red color, this is the gamma ray from open hole logging, and we have in the green and the blue color the gamma ray from core before matching, and in the green color, this is the finally matched core gamma ray of the core to be correlated with the gamma ray from the logging data. Also here we have special core measurements for relative mobility data for different core samples. By applying normalization and averaging workflow, as you can see, all of the samples can be normalized like this from 0 to 1. And we can, by averaging and then denormalizing, we can get the final curve. This is the average denormalized curve representing KRO and KRW and KRO for the reservoir rock type. This is this is all I have in this session. Thank you so much for joining me in this one, and feel free to ask